Now that we have volume or mass conservation, I want to turn our attention to an empirical relationship between discharge, cross-sectional area, and down-glacier hydraulic gradient. This formula is known as the Manning formula, and strictly speaking, it has been tested for open channel, gravity-driven flow down a rough conduit. However, it has been shown to work in a variety of cases in physical settings as diverse as water flow over vegetated plains. It is probably one of the most successful empirical relationships in all of the engineering sciences. So I'm going to follow what a lot of folks do, like Mark Fahnestock. I'm going to lump all of the geometric parameters into a single function. That function happens to have units of discharge, so I'm going to call that volumetric hydraulic conductivity. Doing a little bit of arithmetic, we can then find from the Manning formula that the discharge is related to this volumetric conductivity multiplied by the square root of the down glacier hydraulic gradient. The task we are now left with is determining an appropriate function for the hydraulic conductivity. I'm going to follow Mark Fahnestock and use the following function. It's a product of the background conductivity measured during the background pressure head multiplied by the flotation pressure head less the background pressure head normalized by the flotation pressure head less the present value of the pressure head. It has the following qualitative features, which are physically intuitive. It increases with pressure to qualitatively simulate cavity growth and an increase in conductivity. If we let the pressure fall to the background hydraulic head, it maintains a steady state conductivity, and it becomes infinite if we pump so much water to the basal system that the entire ice floats. So physically, it is in line with our intuitive feeling for what the end member results of the hydraulic conductivity should be. Next, I'm going to summarize all the expressions we have derived or argued for so far and use those to come up with a governing equation for the pressure head. So to begin with, we arrived at an expression for mass conservation. Simply stated, that is that the time rate of change of storage area at the bed is equal to the negative of the down glacier discharge gradient plus a source. After that, we got the modified Manning formula. That was an empirical relationship for turbulent water flow, which gave us the discharge as a function of volumetric hydraulic conductivity multiplied by the square root of the down glacier hydraulic gradient. Last of all, I'm going to present a simple parameterization for storage of basal water. It simply states that the area over which basal water is stored is a product of some storage width, WE, multiplied by a subglacial porosity, mu, multiplied by the pressure head. That has units of area and gives us an appropriate relationship which we can then use to derive an expression that will give us a governing system. Now I can combine these three equations to get a governing system which describes the hydraulic head as a second-order nonlinear partial differential equation. It cannot overstate how difficult these equations are to solve, so to begin with, I'm going to split the hydraulic head into a steady and transient part. That is, I'm going to take the hydraulic head, I'm going to write it as the sum of the background value plus the transient value and do the same thing with the source. Now the steady state part simply says that the background hydraulic head is equal to some constant. However, what it does do is it simplifies our boundary conditions. We can then use homogeneous boundary conditions if our initial condition is such that the present value of the hydraulic head at time t equals 0 is equal to the background value. Now what I'm going to do is assume that the transient hydraulic head is much smaller in amplitude than the steady state part of the hydraulic head. This allows me to expand the hydraulic head in terms of its perturbation series. And all this really means is I take the hydraulic head, expand it as its Taylor series, only retain the linear terms and assume that the higher order terms are too small. And in doing so, I get an advection diffusion equation. What's nice about this equation is that it gives me a wave speed term and a diffusion term. And what it says is that if I have a very small perturbation to the background value in the pressure head, that it will propagate with a given velocity. And not only will it propagate with this given velocity, but the amplitude of this disturbance will also decay over distance. So it reproduces what is actually observed geophysically. If I take the geophysical parameters from the variegated glacier, which Mark Fahnestock studied, that gives a wave speed which is about 1/2 to 2/3 the observed value, but just the fact that it's close of all suggests that we're at least on the right track for coming up with an expression which explains the mechanism through which these pulses propagate. Next, I'd like to show a few snapshot profiles of that pressure. Now, I took these plots simply from a document that explains the Advection diffusion equation in the case where the initial condition describes an impulse. That is, imagine we take a syringe or a giant volume of water and inject it impulsively into the subglacial drainage system. That would result in a Gaussian function which propagates down glacier in the direction of the hydraulic gradient. And as that pulse propagates, it decays and sort of smears out. Now, the one problem with this solution is that it sort of violates our perturbation assumptions of small amplitude and small gradient. However, it does at least show that the pulse propagates and diffuses as it propagates. So this is the perturbation solution. The end result of this modeling isn't to simply find a perturbation solution, but rather just to show the mechanism through which these pulses propagate. Next time, I'm going to talk about modeling of tunnelized systems. And then after that, I'm going to talk about how to solve these nonlinear partial differential equations via quasi-linearization, which is similar to Newton's method, using finite volume methods. Anyone who's taken Ed Waddington's class will be at least familiar with these methods, and it shouldn't be too difficult to jog your memory. My emphasis is to keep the math somewhat at a minimum, and rather to try to emphasize the physical interpretation of the mathematics. So that's it. Thanks for your attention. Thanks for listening and going through the math with me, and I will see you next time.